Properties of vector addition and scalar multiplication. The following theorem gives laws satisfied by the operations of vector addition and scalar multiplication of any vectors in V2. If A, B, and C are any vectors in V2, and C and D are any scalars, then vector addition and scalar multiplication satisfy the following properties. Theorem 17.21. 1. A plus B equals B plus A. We also call it commutative law. 2. A plus the sum of B and C equals the sum of A and B plus C. We call it associative law. 3. There is a vector 0 in V2 for which A plus 0 equals A. We call it instance of additive identity. 4. There is a vector negative A in V2 such that A plus negative A equals 0 vector. We call it instance of negative. Theorem 17.21. 4. 5. CD multiplied by A equals C multiplied by DA. We call it associative law. 6. C plus the sum of A and B equals CA plus CB. We call it distributive law. 7. The sum of C and D multiplied by A equals CA plus DA. We call it distributive law. 8. 1 multiplied by A equals A. We call it instance of scalar multiplicative identity. Proof. We give the proofs 1, 4, and 6 and leave the others as exercises. Let A equals A1, A2, B equals B1, B2 by the commutative law for real numbers. A1 plus B1 equals B1 plus A1. A2 plus B2 equals B2 plus A2. And so we have A plus B equals A1, A2 plus B1, B2. We only need to calculate the corresponding coordinates. So we also have A1 plus B1, A2 plus B2. By using these equations, we have B1 plus A1, B2 plus A2 equals B1, B2 plus A1, A2 equals B plus A. Next, let A equals A1, A2, B equals B1, B2. The negative A given by definition 17.15, and we have A plus negative A equals A1, A2 plus negative A1, negative A2 equals 0, 0. We also call it 0 vector. This is the second one. Next, let A equals A1, A2, B equals B1, B2, and we have C multiplied by the sum of A and B equals C A1, A2 plus B1, B2. We need to calculate the corresponding coordinates of the branches. So we have C A1 plus C B1, C A2 plus C B2. Next, we can put the scalar C outside the brackets, so it equals C A1, A2 plus C B1, B2 equals CA plus CB. Example 1. Verify 2, 3, 5, and 7, and A of failure 17.21. If A equals 3, 4, B equals -2, 1, C equals 5, -3, C equals 2, and D equals -6. Solution. First, we can calculate the sum of B and C. It equals 3, 4 plus -2, 1 plus 5, -3. We calculate this bracket first. So it equals 3, 4 plus 3, -2, 6, 2. Next, we calculate the sum of A and B first. It equals 1, 5 plus 5, -3 equals 6, 2. Therefore, A plus the sum of B and C equals the sum of A and B plus C. So, the second equation holds. A plus 0 vector equals A. It is easy. Hence, the free equation holds. CD multiplied by A equals. We first calculate CD first. So, -12 multiplied by 3, 4 equals -36, -48. C multiplied by DA. We calculate DA first. So, we have 2, -18, -24 equals -36, -48. Thus, CD multiplied by A equals C multiplied by DA, and so the 5th equation holds. C and D multiplied by A. We first calculate the sum of C and D. Equals -4, 3, 4 equals -12, -16. CA plus DA equals 6A plus -18, -24 equals -12, -16. Therefore, The sum of C and D multiplied by A equals CA plus DA, and the 7 equation holds. It's easy. 1 multiplied by A is equal A, and so the A equation holds. Definition: 17.21 theorem is very important because every algebra law for the operation of vector addition and scalar multiplication of vector in V2 can be derived from the A properties stated in the theorem. These laws are similar to the laws of arithmetic of real numbers. Furthermore, in linear algebra, a real vector space is defined as a set of vectors together with a set of real number scalars, and the two operations of vector addition and scalar multiplication, which satisfy the A properties given in theorem 17.21. Following is the formal definition. A real vector space V is a set of elements called vectors together with a set of real numbers called scalars, with two operations called vector addition and scalar multiplication, so that for every pair of vectors A and B in V, and for every scalar C, a vector A plus B and a vector CA are defined so that properties 1, 2, A of theorem 17.21 are satisfied. From definition and theorem, it follows that V2 is a real vector space. We now take an arbitrary vector in V2 and write it in a special form. A equals A1, 1 yellow plus A2, yellow 1, because the magnitude of each of the two vectors, 1 yellow and yellow 1, is 1 unit. They are called unit vectors. We introduce the following notations for these two unit vectors. I equals 1, yellow, and J equals yellow 1. The position representation of each of these unit vectors is shown in figure 17.21. We can see from the figure, I is the unit vector of X. J is unit vector of Y. This is J. Because A1, A2 equals A1J plus A2J, it follows that any vector in V2 can be written as a linear combination of the two vectors I and J. Because of these vectors I and J are said to be form or bases for the vector space V2. The numbers of elements in a basis of a vector space is called the dimension of the vector space. Hence, V2 is a two-dimensional vector space. Let me see the following illustrations. 1. We express the vector 3, -4 in terms of I and J. So, we have the following equations. We also call it 3i minus 4j equals 3, -4. Let A be the vector A1, A2, and theta be the radial measure of the angle given the direction of A. A1 equals the magnitude of the vector A multiplied by cosine theta, and A2 equals the magnitude of the vector A multiplied by sine theta. Because A equals Aij plus A2j, we can write A as the following equations. Equation 1 expresses the vector A in terms of its magnitude, the cosine and sine of the radial measure of the angle given the direction of A, and the unit vectors I and j. Let me see the figure 17.2.2. This is the magnitude of the vector A, and this is theta. Again, this is the magnitude of vector A, and this is theta. Example 2. Express the vector -5, -2 in the form of equation 1. First, let me see the figure 17.2.3. This is magnitude of the vector. First, we can calculate the magnitude of the vector -5, -2. It equals the square root of 29. Sin theta equals -2 divided by the square root of 29. And cosine theta equals -5 divided by the square root of 29. So from the equation 1, we have the following equation. Theorem. If the non-zero vector A equals A1j plus A2j, then the unit vector U having the same direction as is given by the equation 2. Proof. From 2, we can put the magnitude of the vector A outside the bracket. So, we have this equation. Now, we know that A equals A1I plus A2j. Substitute this equation into the brackets. So, we have these equations. Therefore, U is positive scalar times the vector A, and so the direction of U is the same as the direction of A. Furthermore, the magnitude of the vector U equals 1. Therefore, U is the unit vector having the same direction as A, and the theorem is proved. Example 3. Given A equals 3, 1, and B equals -2, 4. Find the unit vector having the same direction as A minus B. Solution: we first calculate A minus B. It equals 5, 3. So, you may write A minus B equals 5i minus 3j. Then, we calculate the difference A and B. We can calculate its magnitude. It equals the square root of 34. By using theorem 17.2.3, the design unit vector is given by the following equations. So, U is the unit vector. That's all. Thank you.